Is this the one?
Oh, okay. Okay, thanks. Okay, I have to make it fast. Okay, thanks for the first speaker to go over the fresh blood imaging. I would like to mention a little bit about the background of fresh blood imaging, which uses the physiological signal difference of systolic and diastolic phase for subtraction, and coronal acquisition, unlike the time of flight, so that the body is shorter in the superior to, front to the back side, so slice encoding is smaller compared to time of flight. And flow speed difference in iliac and femoral and cuff station, Dr. Philip just asked, we can use the different spoiler pulse to knock down the unwanted systolic signal to bring the signal, contrast up. I can explain that later. Okay. This slide showed we don't use the signal difference, just bring it up so that you can see the systolic intrinsically signal is lower because of intrinsic dephasing effect, and diastole has a higher signal intensity. No pointer? Okay. Well, so the systolic and diastole subtraction gives the arterial image. I just wanted to show you here that explaining this flow compensation and flow dephasing, when flow is faster, you don't need to, we need to flow compensate, otherwise it's intrinsically voided, flow voided. So we use the partial flow compensation, like on the top, and iliac station or femoral station. And for when flow is slower, we use intrinsic, the spoiler pulse, so that systolic will help decrease the signal for the artery. And we subtract, we use systolic and diastolic. It's not interleaved manner, just simple systolic acquisition followed by diastolic and automatic subtraction. This have a meaning because when you subtract, if you do systolic and diastolic, you have a different recovery time, so your background signal will be different. So we use just simple continuous systolic triggering followed by diastolic slice encoding, and system does automatic subtraction and MIP. Okay, this was a study done by Dr. Nakamura using this different flow spoiler pulse. For healthy volunteer, flow is faster, so we use minus 10% gradient pulse for partial refocusing. And for femoral, normally 0, and popliteal region, we use the stronger spoiler pulse. For elder patient, flow is slower than compared to the healthy volunteers, so we use stronger pulse. And this is, actually the paper was 1.5 Tesla. This was obtained by 3 Tesla. We overcome with many issues, but because of the nice signal in 3D, we give us the very nice images of FBI. However, there is the intrinsic problem compared, using this FBI, like previous speaker mentioned. Takes about 4 to 6 minutes. Actually, at 3D, it's longer because 3D has a longer T1, and the parameter is showing like this, 1.3 by 1.3 by slice reaction 1.6 millimeter. Takes about 4 to 6 minutes. And N/2 artifact is prominent sometimes for faster flow, especially at the iliac station. So we adapt to make it faster. We should have less problem of motion. So we adapt this KYKZ scan. The original one acquire every slice encoding followed by the phase encoding. But in KYKZ, we mix KYKZ direction and use the half Fourier, and we don't acquire the corner of the K-space, and that makes shorter scan time. And this is the FBI, standard FBI compared to centric FBI. You can see in subtracted source image shows the n/2 artifact. And centric FBI shows less those n/2 artifact. And scan time has been, depend on the ECG RR interval, but scan time has been reduced to 1/2 to 1/3. And this is another study for the n/2. If we use the stronger dephasing pulse, then we introduce n/2. But in FBI, centric FBI, we have a less n/2 artifact. Another problem is that at 3T flop angle or refocusing flip angle, is if it's high, then scan time is automatically elongated because we like to use like 3 RR or 2 RR interval, but because of SAR shift that RR interval to like 4 RR interval, which scan time is longer, even though your acquisition window is short because of SAR, that's will increase. But using the parallel imaging can bring down a little bit too. So we use the high flop angle until like 49 or 50 echoes, first echoes, so that your flop angle is high when you catch those fast flow and maximum flop angle. And then peripheral of the case space, you can lower it so you can reduce the SAR. And the left slide shows the flop angles that going down from 180 to even 0 degree. And what's happened to the decay of the signal compared to constant flop angle and exponential flop angle. You can reduce the flop angle to, you can keep the signal, but you don't need for the later echoes. So it has the intrinsic T2 plus or shortening T1 recovery time. Sorry, it's not going. Sorry, okay. This shows the difference in flop angle, and the constant flop angle gives 3 minutes and 9 seconds, and lower flop angle gives less than 2 minutes scan for this femoral station. And the depiction is very similar. So the reason of less than 2 minutes for all this flop angle because of the SAR is lower, so we could acquire in 2 RR interval. In conclusion, centric FPI with the exponential flop angle allows a tremendous reduction of scan time, n/2 artifact was diminished, almost diminished, and which was prominent in standard FPI. And clinical evaluation will be performed shortly. Thank you for your attention.